Hi, everyone. Sorry about the Zoom link, but hopefully that works now and everyone saw my new announcement. But welcome. Today we're just gonna do like a 1 hour review session. I'll stay a little bit later just so we get the full hour. But this is your time to ask any questions you may have for your exam. If you are in Dr. Bengali's class, you are taking your exam on Thursday, and if you're in Dr. Altamos's class, you are taking your exam on Friday. You take that in class. Dr. Bengali's all multiple choice, and then Dr. Altamos is multiple choice with a couple short answer, just like the last exam. Other than that, I think that's all the announcements I have. For the review questions that I posted yesterday, that answer key will be posted tomorrow morning. So just try that on your own first, and then you can check your answers tomorrow. I think that's it. What questions do we have for me? Is there anything you'd like to see to go over? And you can just use the chat or take yourself off of mute.
Can we go over chapter 6 material?
Yep, absolutely. So is there anything specific from chapter 6?
Just kind of general. I really didn't do too well on the quiz, so I just kind of want to cover everything.
Yep, absolutely. So can someone remind me what, yeah, I just started it like 2 minutes ago. So can someone remind me what chapter 6 material is? What did we talk about in chapter 6?
Electron configuration was one of them.
Yep, so we have electron configuration, right? This was all like your light and your electromagnetic spectrum. Right, all of this fun stuff came in chapter 6. Okay, so when we talk about electromagnetic spectrum, right, we should know our electromagnetic spectrum, but this is categorized from high energy to low energy. And what is associated with a high energy wave? What kind of frequency and what kind of wavelength?
High frequency and low wavelengths.
Perfect. Right, so we have high frequency and we have low wavelength. And that means at the opposite, at your lower energy, you have a low frequency and a long wavelength. I guess this is more short, right? So our high energy waves, that's going to be our gamma rays. They happen really, really tight together. They're oscillating very quickly and their wavelength is very short. But on your low energy, that's going to be like your radio waves, right? Those are very long. They have to go around buildings. So those do not occur as frequently, or they don't oscillate as quickly. And that means that their wavelength between, 2 points on the wave are longer. Which way does our visible spectrum work? Is your red closer to the low energy or the high energy? Good, right? So you have your red light on this side, which means you have your violet light on this side. Okay, so just keep that in mind. When we talk about electromagnetic spectrum, right, we have our speed of light is equal to the wavelength times the frequency. We have our energy is equal to Planck's constant, which would be given to you, times the frequency as well. We can combine these and say that this is energy is equal to hc over lambda. All right, all of these are given to you, but these are just what you should be thinking if you see some type of question and that involves waves. We also know the de Broglie wavelength, which is the wavelength is equal to Planck's constant divided by mass times velocity. And mass here is in kilograms and velocity here is in meters per second.
Is Planck's constant in joules per second?
Yes, yep, this is going to be 6.626 times 10 to the negative 34 joules times joules per second. Joules or seconds. Or joules times second, joules times. The energy or the unit should be given to you along with the constant on your formula sheet. So just double check, make sure that I'm not messing that up. Alrighty. What else we talked about in chapter 6 were energy levels. Okay. So if we have an energy level, if we're starting at n is equal to 1, what do we call n is equal to 1? Or that lowest energy level?
The first energy level?
Think more. Okay, so let's just think.
Ground state.
Yeah, perfect. Right, so that's going to be your ground state. This is your lowest energy, right? Sometimes it doesn't necessarily have to be into n is equal to 1 for hydrogen. That is correct. But your ground state is where all of your electrons are in the lowest energy state possible. If we wanted to go to an excited state or a higher energy level, what do we have to do in order to do that?
Absorb.
Good. So in order to go from a lower energy level to a higher energy level, whether that be 1 to 3, 2 to 4, 3 to infinity, right? We have to absorb energy. And what happens when we go back down to ground state, or we go back down to a lower energy level?
Emission.
Good. So we have to emit something. In this case, it's a photon that is released that has the energy that's the difference between those two energy levels that it's transitioning between. Okay, we know that those energies are quantized, so there's a specific energy for each of those specific energy levels. So the difference to get from 1 to 5 would be the sum of, 1 to 2, 2 to 3, 3 to 4, 4 to 5. Anything else from light that anyone can remind me of or think that I'm missing? I think that's the big stuff there.
Was it something with like NL and
Yep.
like electron domains and all that?
Yep, perfect. So that moves into quantum numbers. So we have N, L, M sub L, and M sub S. What does N tell us?
Energy level.
Good, this is your energy level. This comes from the period on the periodic table. So if you're just reading across, right? Oxygen is in the second period. That means it's in the second energy level. What does L tell us? Good, that's the shape. What else do we call the shape? How do you identify? What's another name? Yep, it's going to be your orbital type. Right, and so what options do we have? L can be equal to 0. And what does that equal? Or what orbital does that correlate to? Yep, this is going to be S. When L is equal to 1, this is going to be P. Great. L is equal to 2, this is going to be D. And when L is equal to 3, this is going to be F. Someone does have this correct. L must be n minus 1. So if you're in the first energy level, then the only option for L that you have is 0. If you're in the fourth energy level, when n is equal to 4, L can be 3, 4, or sorry, 3, 2, 1, or 0, right? Anything less than n minus 1. What about n sub L? What does that mean? Yep, good. This is your orientation. And what is our rule for m sub L?
Can be from negative L to L.
Good, so this can be from negative L to L. That includes 0. So if L is equal to 3, then m sub L would be equal to negative 3, negative 2, negative 1, 0, 1, 2, 3. So someone just asked what orientation means. This is how it is laid out around the nucleus. So if you think about the p orbital, there's 3 subshells that it can be in. It's going to be, right, if L is equal to 1, then m sub L can equal to negative 1, 0, 1, which means we have 3 orientations. So this is like thinking about the X, the Y, and the Z plane. So think about your dumbbells going across the X-axis, the Y-axis, and then coming out towards you on the Z-axis. And that tells you the orientation around the nucleus of where that electron could be. Your subshells are going to be your orientation. And if I'm saying something wrong, just please correct me. So that's a great question. The rule is that L can be less than or equal to less than or equal to n minus 1. So it can be 3, but that also means it can be 2, it can be 1, and it can be 0. Because when you get to the fourth energy level, you have the S, the P, the D, and the F that you can all occupy. Okay, thank you. So sorry, your L is your subshell, and your m sub L is your orbital. I do know they like to ask that. So thank you. Okay, does that make sense of the options for 4? So the total number of subshells within n is equal to 4 is when you have 3, 2, 1, and 0. So this is 7 when L is equal to 2. This is 5. L is equal to 1. This is 3. When L is equal to 0, this is 1. So your total number of orbitals is 16 orbitals. And the n is equal to 4 energy level. So that occurs in the, what do you mean by being taken away?
Sorry, like when I just don't understand like in what I remember the rule that for some reason somewhere when you're taking away orbitals when you're trying to make I think it's when you're trying to make ions or something like that, or when you're going from or like I can't remember when that rule applies. Yeah, excited state configurations, thank you.
Oh, yes. So let's finish up quantum numbers and I'll tell you where that comes into play real quick. So for m sub s, just to round it out, right, this is going to be your spin. And this is always going to be +1/2 or -1/2. Right, and this comes into play with electron configurations because in an orbital, what do we do first with our electrons? Do we pair them or unpair them? Good, you unpair. Right, and then you're going to pair. 2 electrons in the same orbital cannot have the same spin. You can't have 2 up spins and you can't have 2 down spins. So your down spin will be -1/2, your up spin will be +1/2. By convention, usually the up spin goes first. So if you're going to write a quantum number, usually do the up spin first. Alrighty, any questions?
On the mock exam, it said if we added an m sub s 0, it changed like how many electrons could be in the 1s and 2s configurations. How is that possible?
What question was that?
Give me 1 second.
Yep, no problem.
Number 12.
Okay, so what we're saying here, right, is now if we can have a third spin. So we're saying that in the, right, if we just look at the S, how many orbitals are in the S subshell? How many orbitals? Yeah, right, we just have 1 orbital. So now we're saying, right, so now we're saying that usually we have an upspin and a downspin. But now our S1 orbital can have an upspin, a downspin, and then a 0 spin. So now we can, the first 3 electrons go into the S orbital instead of the first 2 electrons, right? So instead of 1s2, 2s2, 2p4, is that carbon? 2p2. Yeah, 2p2. Now it's going to be 1s3, 2s3. Because now it's going to build up 1, 2, 3, and then 1, 2, 3. Not 1, 2, 1, 2, 3, 4, 5, 6. Does that make sense, Aaron?
Yes, thank you.
Okay. Yep. Okay. So then back on the d orbital. So in period 4, we have our first 2 elements, and then we have the transition elements. Okay, so this would be 4s1, 4s2, 3d1, 3d5, right? Stuff like that. Everyone follows where I am on the periodic table. So when we get to looking at electron configurations here, when we have something where it's the 4s2 is filled, and then we have 3d4, where 4 out of our 5 orbitals within the d orbital are being occupied. It's actually more beneficial for this unpaired electron to jump up into this unpaired or unoccupied orbital. So then it turns into 4s1 3d5. Yep, that's for stability. So, right, think about how you want the lowest to exert the lowest amount of energy possible, right? That would be laying horizontal at all times. Right, in the 4s2 3d4, that's like laying horizontal, but you're sitting up a little bit. When you go down to the 4s1 3d5, then it's like you're completely laying down again.
Is
Yep,
it
so that makes it the same for the 4s2 3d9. It's actually more stable to have all of your electrons paired in the d orbital than have it paired in the 4s orbital.
what are the two elements that have exceptions? Isn't it copper and manganese?
Yes. Look at a periodic table. Yep, it's chromium. Sorry, element 24. Is that correct?
And it's gold, right? Or
And then copper. Yep, so copper, silver, and gold, right? That's all in one group. So those will all act the same. Chromium, molybdenum, tungsten, and whatever Sg is. Seaborgium, I guess. Those would all act the same as well. You really will only be asked about chromium and copper though. Does that help with the d orbital in that question earlier? That's just for the orbitals within the 4s2 3d9 and 4s2 3d4 rows. So like if it's 4s2 3d3, it's not going to hop up into the next one. Any other questions on this? Okay. And then I think the last bit about chapter 6 is just electron configurations. Right, this is your building up of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, right? That's about as high as you really need to go. So when you get to a complete octet, that's going to be when you have your 8 valence electrons, and then you can start using your noble gas. So right after helium, then copper could be, sorry, not copper, carbon could be helium, 2p, sorry, 2s2, 2p2, right? So you're saying go to helium and then go these extra electrons to get to carbon. Right, and that can work for anything else. Once you can use your noble gas configuration and you chop up everything that's in your inner radius of your atom, and then you just get the valence shell. That's everything outside of it. You shouldn't be asked about the F block. Just know that it exists and know how to answer questions about it, like if n is equal to 4, or how many orbitals are in the F block, but you don't necessarily need to work up all the way to the F block. This will be recorded and posted. Yep, so when the elements have the same number of electrons. So if we're looking at neon, fluorine minus, and sodium plus. How many protons do each of these have? How many protons does neon have? Yep. How many protons does fluorine have? Great. Okay. How many electrons do each of these have? Perfect. Right? These all have 10. So when we look at the ratio of protons to electrons, right? Think of your proton as a owner holding a leash to their dog, right? When we have 10 protons to 10 electrons, that means that every owner has one dog on their leash. If we have 9 protons to 10 electrons, that means that one owner is doing double duty and holding 2 electrons with the same, or holding 2 dogs with the same leash, right? That's going to be a little bit more unstable. It's going to be a little bit harder to hold on to. On the other hand, if we have 11 protons and 11 electrons, that now means that we have 11 owners and 10 dogs. So now one owner can hold on to one dog the same or kind of help out all around. So when you have more protons than electrons, they have a stronger hold on those electrons. And therefore this gets smaller. Those protons at the nucleus can pull those electrons in closer and hold them tighter. When compared to your fewer protons compared to electrons, they have a less tight hold. And so this one gets larger. And it can expand and escape out a little bit farther than the 10 to 10 or the 1 to 1 ratio. So if you're going to do atomic radius, your largest is F minus, and your smallest is sodium plus, and in the middle is neon. That means that what's next? Magnesium, right? If magnesium 2 plus was in here, we now have a 12 to 10 ratio. So that's going to be even smaller than your sodium ion. Because we have even more owners to dog ratio. Does that make sense with atomic radius and same protons, different electrons? Great. Okay, other periodic trends, atomic radius in general. As we go across the periodic table, what happens to atomic radius? Good. Atomic radius decreases, and as we go down the periodic table, what happens to atomic radius? It increases, right? And as we have a higher proton to a higher electron ratio, we're staying in that same shell going across. And so we're just adding more protons around that valence shell. There's nothing else extra that it has to reach out farther to, and they can pull it in, and the protons in the nucleus can pull those electrons in closer to it, decreasing the radius. As we go down the periodic table, we're adding shells each time. And so our shell and our atom just keeps on getting larger and larger, right? We're drawing more and more circles. So we have, right, bigger and bigger circles with each energy level that we add. So your atomic radius is going to increase. What about electronegativity? Across the periodic table, what happens? Good, this increases. And as we go down the periodic table, what happens to electronegativity? This one decreases, yep. So where's our most electronegative atom? Good. That's going to be fluorine in your top right corner. if you need to find out like what the difference between electronegativities are, which one's going to be more polar, they will give you the values of electronegativity for each atom, and then you can just subtract the two. Electron affinity and electronegativity are two different things. Electronegativity is how badly or how much does the atom want that electron, and then electron affinity is the ability to put that electron on the atom. Okay, and then ionization energy, but the trend is the same for both of those. For ionization energy, as we go across the periodic table, what happens? Generally, it increases, yes. As we go down the periodic table, what happens? Great. Right, and we think about going down the periodic table, it's getting larger and larger. Those electrons are farther and farther away from the nucleus. It's going to be easier to pick it off. As we go across, this is where we have a little bit of an exception. So for, let's say, we'll do sodium, and then magnesium is going to be here, right? So 1, 2. And then it goes, because we now have completed our s orbital, right? Those two electrons are paired. Now that it's paired, it's a little bit stable. And it's going to be harder to pick off that electron. When we go to aluminum, we're now entering a higher energy level orbital, and it's unpaired. So that means that aluminum is going to actually go down in ionization energy. So it's easier to remove the electron from aluminum than it is from magnesium. After that, right, we're adding electrons. And so once we have a full p orbital, it's going to be the highest in order to a full unpaired p orbital, right? That's going to be pretty hard to remove. But then when we look at sulfur, right, this comes down a little bit because now we've paired an electron. So we have one paired, two unpaired. That's a little strange. But then we're going to jump up back to chlorine. And chlorine is going to be really, really hard because there's only one electron away from reaching its noble gas or filling its valence shell. So chlorine would rather have an electron put on it than get rid of it. And then argon is going to be the hardest because that has its full valence shell. It's happy. It doesn't want to do anything. It doesn't want to give up its electrons. So your trend goes up, then down, then up again. Up, then down, then up, then down, then up again. Excuse me. So overall, generally increases, but it is a little slight exception. Okay. Any other questions with periodic trends? Okay, when we look at hybridization, right, we're looking at electron domains here. So when we have hybridization, you just need to identify what the hybridization is, okay? And like what your hybrid orbitals would be. So if we have something like carbon dioxide, how many electron domains do we have? Good, we have 2 electron domains. So that means for hybridization, we need 2 orbitals. What are those 2 orbitals going to be? Good, that's going to be sp hybridization. If we have this here, how many electrons domains do we have? Good, we have 3. So how many hybrid orbitals do we need? We need 3 hybrid orbitals. What are those 3 hybrid orbitals going to be? Good. sp2, right? We have 3 p orbitals that we can choose from. We only need 2 of them. So we're going to always use the s and then use as many p orbitals as we need. What about this is how many electrons domains do we need? Yep, so what is going to be our hybrid orbitals? Good, this is sp3. So Daryl, I don't think you really need to know what they're going to look like or what kind of energy they're going to give off. It's mostly just going to be your concern is going to be like, what would those hybrid orbitals be? Not necessarily like what the mix-up would look like. Right, like for regular orbitals, you need to know that the s orbital is spherical, and you need to know that your p orbital is dumbbell shaped, and then your d orbital is clover, but you don't need to know what those hybrid orbitals are. Yeah, and then in terms of energy, right, it's an average-ish of the orbitals at play. So like between the s and the p, when you have just sp hybridization, it's like the average of the s and the p. When you have sp2, the average of those. And if we have sp3, it's the average of those 3. So you don't necessarily need to calculate or know what that energy is. Just know that it's at a lower state than if it was in an s and a p orbital. Sp is going to be in the middle. Yeah, I believe it's like weighted average where you would have a little bit more pull from the p orbital than the s. Yep, of course. Right, but you just need to really identify what the hybridization could be for that central atom. So as long as you can identify the electron domains, you should be fine. I don't remember, someone asked if Dr. Bengali went over hybridization. I think he touched on it briefly, but I can't remember off the top of my head right now if he really did cover it. If it's not on your mock exam, don't worry too much about it. This should be enough to cover it. Okay, yep, and then we talked about Lewis structures. Okay, so when we look at Lewis structures, right, this is going to give you a visual representation of what your molecule is going to look like. Right, you can have your easy ones like water, ammonia, at this point, SEF4 is easy, right? Just when you have 2, maybe 3 elements, you're able to draw it pretty easily. If you have something a little bit more complicated, like methanol, and you need to draw the Lewis structure, or ethanol even. Right, what I want you to know when you're reading elements or compounds like this is that they're saying this is the central atom, whatever element is first, and this is what's attached. Okay. This is then attached to central atom. And then this is attached to element next to it. Right, so carbon is going to be your central atom here. And you have 3 hydrogens attached. Your next one is going to be oxygen. That means that's attached to your central atom. And then the H is attached to your oxygen. All right, if we look at ethanol, this is going to be your carbon attached to 3 hydrogens. Your carbon is attached to your central atom, and that becomes, sorry, this is 2. And that is attached to your central atom, and then your oxygen, again, is attached and attached. So you can even have something like this. And you can draw it out where it's like that. Great question. So the hydrogen is going to attach to the oxygen because if we look at the number of bonds that carbon has here, how many bonds does carbon have? Yep, it has 4. How many bonds can carbon have? 4, right? It can only have 4. It's only in the second energy level. It can only have the s and the p orbital. It cannot expand its octet. So if we attached the hydrogen here instead of here, we would now have 5 bonds to carbon, and you can't do 5 bonds to carbon. The way that this is written, if it's written out condensed like this, it would be attached, right? Like if this was CH3SH, right? It's still going to be attached to that element that comes right before it. Does that help answer your question, Daryl? Yep, so if this was then SH3OH, it's still written as the S gets attached 3 of the hydrogens, then you attach the oxygen, and then you attach the oxygen, or you attach the hydrogen to that oxygen, whatever comes right before it. If it's going to be attached to that central atom, it'll be the next element that comes right afterwards. Yep, and this is usually what we write for hydrocarbons or just like organic material that just has carbon, hydrogen, and then maybe 1 or 2 other elements. So you shouldn't see anything too crazy where you're going to be attaching it back to the central atom. Yep, so when we look at intermolecular forces now, right? When we look at ethanol, all right, or methanol, I'll write that again. Do we have polar bonds in our electron or in our molecule? Yep, where are our polar bonds? So C to O is going to be polar. What is more electronegative, carbon or oxygen? Good. Anything else where we have polar bonds? Good. O to H, which one's more polar? Good. And then someone did say carbon to hydrogen. And although by itself, just carbon to hydrogen is not going to be a polar bond. Those have the same electronegativity, just on its own. When you have the situation here where the oxygen is now attached to the carbon, we're going to pull some of that electron density towards the oxygen, making carbon slightly positive, which is then going to have little tiny baby effects on these polar bonds here. So the hydrogen is actually going to have a little bit of a polar bond. But you could call those nonpolar. That's just like kind of technically what's happening if you're going to move into organic chemistry. That's what that looks like. But your two main important polar bonds that you would have to show are going to be the carbon to oxygen and the oxygen to hydrogen bonds. What type of bonding do we have with methanol? Like what intermolecular forces do we have? Yep, we have hydrogen bonding. What else do we have? We have dispersion. Good, and we have dipole-dipole. Okay, what's going to be our strongest one here? Good, hydrogen is our strongest. What's going to be our weakest? Dispersion. And then the dipole-dipole is your medium range, right? Hydrogen bonding is going to be more Hydrogen bonding is stronger than dipole-dipole interactions, because it can interact with other hydrogens and other nitrogens, oxygens, or fluorines, that it might be attached to. All hydrogen bonds are dipole-dipole interactions. So if you have a hydrogen bond, you do have a dipole-dipole bond, but not all dipole-dipole bonds are hydrogen bonds. So you can have dipole-dipole without hydrogen, but you can't have hydrogen without dipole-dipole. The hydrogen bond is going to be here, this OH, because what is our criteria for hydrogen bonding? Yep, so hydrogen must be directly bonded to a oxygen, nitrogen, or a fluorine. Right, so you can't have carbon, oxygen, carbon, hydrogen. This is no hydrogen bonding, but carbon, carbon, oxygen, hydrogen. This is yes to hydrogen bonding. Yep. So then how do we know what intermolecular forces are there? You will always have London dispersion forces. So if all else fails, London dispersion forces do exist. If you have a polar molecule, then you have dipole-dipole. Right? Overall, you have dipole-dipole interactions. So something like water. Let's do a different example of that. Something like H2S. These have polar bonds across the sulfur hydrogen bonds. And right, so this has an overall polarity here. So that will have dipole-dipole interactions with other compounds that have dipole-dipole interactions, or will have dipole-dipole interactions with itself. And then if you have OH, NH, or FH, then it's hydrogen bonds. if you have anything like sodium plus close to a water molecule, right? Anytime you see something with a charge, with a full charge, right? This is a full charge. This is when you have an ion dipole interaction. The same as if you had magnesium 2 plus close to H2S. Right, this is ion dipole interactions. Yep, so you identify a polar molecule by the net dipole moment. So right, you have to pay attention to the symmetry of the molecule, the electron, the lone pairs that might be around the central atom of the molecule. But just look at your vectors from your dipole moments, and then you can determine if it's overall going to be polar or nonpolar, right? And that comes from your shapes, and where the lone pairs are around the central atom. Full charge means if it's plus atom or a cation or an anion. So this would also work for chlorine minus, right? That full charge means a full plus or a full minus. Lone pairs will not necessarily create dipole moments. It will cause the symmetry of the atom or of the molecule to falter. And then that might create an overall dipole moment. But only dipoles come from the bonds between two elements, and then the lone pairs then screw up the symmetry of the atom, creating the overall dipole moment. Bonds that have nonpolar molecules are the same element bonded to each other, like carbon attached to carbon, or carbon attached to hydrogen. Someone asked about dispersion forces. So the larger the molecular weight of an atom, the larger the London dispersion force is. So technically methanol would have weaker London dispersion forces compared to ethanol. So this one would have the higher boiling point. So larger molecular weight equals greater London dispersion forces, which means higher boiling point, which means lower vapor pressure. Okay, and then, so when we look at symmetry of an atom, so if we have something like methane or CH4, what is the shape of CH4? Good, this is tetrahedral. Right, and I said in my review session on Wednesday, right, that I think of tetrahedral as a tripod, right, your 3 legs, and then with a phone on top, so you have your 3 in 1. 2 of them will be in the plane, and then 2 of them will be, one will be, excuse me, one will be coming out from you and one will be coming towards you. So in this case, since all of our bonds are the same, right, it's always a carbon attached to a hydrogen, all of your interactions and your any dipole moments that may exist would cancel out because your vectors are all pointing in equal and opposite directions. So this one is symmetrical. If we talked about carbon attached to 2 fluorines and 2 chlorines, here I drew it so that it doesn't look symmetrical, right? You have your fluorines pulling to one side and your chlorines pulling to the other. but this shape is still tetrahedral. And what is the difference between, or I guess, which one's going to have a greater polarity difference, carbon to fluorine or carbon to chlorine? Good, carbon to fluorine. So you have stronger dipole moments moving this way than compared to your carbon to chlorine. So because your vectors are not going to cancel out, even though they're all pulling out, your fluorine dipoles are going to pull more than your chlorine molecules, creating a net dipole moment towards the fluorine molecules because it's no longer symmetrical. Ivana, nope. So if it looked like this is still not non-polar, right? This case we have your big dipole moments this way and your littler ones this way, but this doesn't cancel out because it has to think of this as a three-dimensional shape. So in your right tripod, if you look at it like this, maybe this is carbon and then my thumb is carbon, or sorry, my fist is chlorine and my thumb is chlorine. So those are going to pull out this way, but my two fingers down here are going to be my fluorines and they're going to pull this way. And overall, your fluorines are going to take over and they're going to pull in this direction. So they still don't cancel out because you have a three-dimensional shape working. Does that make sense? And then the last thing that we could look at, you need to know what those shapes look like. Yes. So you need to know what you need to kind of visualize or be able to write down what a tetrahedral looks like or what a square what a bipyramidal does. Trigonal bipyramidal, excuse me. Or like what a octahedral looks like. So right, when we have trigonal bipyramidal, this is saying that we have a triangle up top, or I'm sorry, a point up top and then a triangle at the bottom, right? Triangle here, consider this. So it creates a point to all three of these, right? We have one triangle coming up. We have another one going back like this. So it's the two going up and down, right? So when we talk about trigonal bipyramidal, your what positions come off first? Your axial or equatorial? Here, axial can get removed. So if you have something like this here, right? This is that seesaw. You have your two, I'm sorry, this is not axial, this is equatorial. Right, seesaw, you have your two elements in the axial position and two in your equatorial position, creating that seesaw shaped. Then you can have this one here. You have two axial, one equatorial. And then you can have one that has three lone pairs and two bonds. These are now just going to be in the axial position, and this would be a nonpolar molecule because all of your lone pairs are on the equatorial position, and they can cancel out any of the spacing between them. So this one is nonpolar, even with lone pairs. It's linear. I just drew my my bonds looking a little bent, but this is linear. And then the only other time that happens is if you have octahedral. Here you have lone pairs axial bonds equatorial. Yeah, in order to create your bonds, or in order to allow your bonds to be the farthest away possible with that lone pair taking up more space, it's best for the equatorial to be removed first in the trigonal bipyramidal. But for your octahedral, it's then axial that is removed first. Alrighty. I think that about does it. Are there any other last minute questions before? Jackson, so you really just need to know that tetrahedral is like 109.5, and then the ones with the lone pairs are less than that. Trigonal bipyramidal is 120 and 90, and then octahedral is all 90. Yep, so then square planar, this is nonpolar. Assuming that everything that's attached to that central atom is the same element, right? If the second that this becomes, right, X's and Y's, then all bets are off. That's still a polar molecule. There's transition elements, but follow your octet rule always. And usually you'll be asked about the octet rule for periods 2 and 3.
What is the structure of the one that's to the left of the linear diagram?
This is T-shaped. This is seesaw. Oh, she left, but I think I just understood what her question was. The octet rule is once you get to period 3, right, then that can expand its octet. So once you get to period 3, it can have more than 4 bonds. Okay, anything else? Alrighty, we'll call it good there. And then if you have any further questions, just send me an email or come see me tomorrow in Heldenfeld's room 111. And then good luck on your exam if I don't see you until then. And I'll post the answers to my review questions in the morning. So the last example here is that I'm saying as long as the central atom is attached to on the outside by the same element, it's nonpolar. But if your central atom has different things attached to it, then it might not be nonpolar anymore. Perfect. Alrighty. Thanks so much, everyone. Good luck. See you tomorrow.